Is it good evening or good afternoon? Good afternoon, members. We have been visitors from where they keep time. We are deciding to make sure that we do not miss those who have come early. So we shall spend some time in the prison trees as we wait, but when we are trying to socialize. So the agenda is not so tight. I have to look for it. Okay, my names are Benefit. I'm in physics, and I will be playing as an MC for today. I normally say I'm a part-time MC. Amidst us, each one will be able to say something, but I have to introduce them. On the immediate left is, should I say the one starting with P? Okay. Okay, it's Miss Margaret Ann Rwampamba, and she works with the National Science Foundation in the United States. So she's a United States government worker. So in a way we are dealing with someone who's from the United States government. And it's the reason we are here. But because of her experience, she was able to get us somebody who can come and give a lecture and share the knowledge from another place. But she will say something more about her motivation, her work, and what has led her to be in this direction. Next is a common face, is my boss at the college, Professor J. White, magician. We also get an opportunity to say something to us. And next is our presenter, Professor M.C. Spencer, NT, ND, oh, C and D. My mind became a bit slow. And he will present how they functionalize surfaces in materials. And I don't want to poke into his presentation. He still has enough time for that. The last on the table is my immediate boss, Dr. Winston Klopsilater, the head of Department of Physics. It's a long story on how we have come to be here on this kind of lecture, which long story we shall be able to share later on. For now, that you know people on the front table, I will drop the microphone down, and as we wait, because we decided that we shouldn't just sit and start chatting as we wait for other people, but we are a good number. We would like to know people who came early, people who are punctual. So you tell us your names. I'm going to bring the mic. You tell us your names, what you do, and then we shall be ready to start on time as we have done. In that respect, I will have to invite my boss, immediate boss, to give us a small synopsis of the visitors and the event in general, and then he will take an opportunity to invite his immediate boss, and then thereafter Margaret Ann will be invited, and then being that she's a colleague to the presenter, will be the one to invite the presenter so that we can get the main cause of being here. You're welcome, sir.
Thank you, Benon. Our presenter, Professor Nicholas Spencer, is a world-renowned scientist and is the current president of ETH Research Commission in Zurich, that's Switzerland. He's also the chair of Laboratory for Surface Science and Technology at the Department of Materials at ETH Zurich. I got to know him through Margaret. Shall tell you about that one. Through Margaret and first we have met Margaret before, the department. She's been so instrumental in Africa materials science workshops and schools. So she has been helping us a lot with getting funding for students to go and do and attend schools and workshops in Africa. Nicholas arrived in the country on 2nd January and has been traversing the country. Now he knows Uganda more than some of us, those who travel. He's been with us for 2 days now, came yesterday. And we have met various officials in the university. Those who have started strong collaboration with this institution. So it's going to give us public lecture, which you can see the title, and the abstract, for those who didn't get a chance to read it somewhere, is surfaces are crucial in determining many materials properties, whether it be their lubricity, their biocompatibility, or their resistance to corrosion. So in this case, if you attach the attachment of small organic molecules and polymers to material surfaces is an invaluable approach to tuning such properties. So in this presentation, you see how surface functionalisation can be performed on a host of different materials and how it can be used to produce surfaces and surface structures that lead themselves to specific applications. This is our Union for the first part of Africa English lecture series, and we hope that we shall be holding these lectures every year, or maybe 2 or 3 every year. But it's a baby for Margaret, and we also have to thank Professor Spencer because he sponsored himself to come here. He's come for all this time. All we have done is just the advertising, buying the water, and getting the officials. But he sponsored this accommodation, the ticket, everything. So, and he says he's willing in the future to create a pool whereby he can identify for us different guests or distinguished professors to come down here and share with us knowledge and maybe also get those collaborations between students or staff and this institution. So now it's my pleasure to invite my boss. It's not my immediate boss. It's my boss because there's someone in between. There's a dean, the principal of the College of Natural Sciences, just something, then I'll ask you to invite Margaret. She can say something also. Thank you.
Good afternoon, all of us. You're most welcome to the College of Natural Sciences. I know we are now in another college, but the purposes of venue, but you are all visitors of the College of Natural Sciences, and the Makerere University is honored to have you here. We want to wish you a good stay, and maybe to say that you should have the best of 2015. My head of department, Dr. Rebecca, Professor Spencer, and Margaret, for this that the target sector, of course, I not to say a couple of other names. And then the MC, thank you for organizing this event. Some of us are down in 2 chairs, so by the time we come to know this, it is at the very last moment. So we want to thank those who have put in effort to ensure that we have this, particularly and for the interest that you should have this series of the first Pan-African distinguished lecture series. I wish to see this lecture series remain in science, of course, as a scientist and as the first lecture that you have brought to us. We want to thank you so much for choosing Makerere to have this first distinguished lecture series. And this chapter will come our first distinguished lecturer and Professor Spencer for accepting to come and be with us here. Uganda is a nice place. You probably could have seen we came at the right time of the weather that is so good and generously full of green everywhere. And we want to yourself. Next time, please go ahead and support yourself and come. I have discussed with the visitor and the head of department to come along to have a call in my office. And we have a lot in common as an institution. Mackay University will wish to see that we continue with this collaboration. We want to welcome you here on behalf of the university and wish you all the best. Thank you so much for choosing time. And I invite Anna to come and maybe say. And also thank you very much once again for the interest in physics and the ensuring that you bring this event here.
Thank you very much, Professor. I don't have a lot to say, apart from just complimenting you guys for having put in my effort to start this lecture series. The idea came from the fact that back home in the United States, we have lecture series in each and every discipline of science. They are all called distinguished lectures, and they are all performed by professors like Professor Spencer, who goes around the country in the United States and give their lectures and update the students in that country, in our country, and faculty on all the research they are doing. That's the only way they can keep up with the scientific research that is going on in the United States. So I thought that it would be a very good idea for Africa. East Africa is my birthplace, so I have compassion for this region, to start this lecture series, and you can expand it to Kenya and Tanzania. That is my dream. And then you, the three countries, can collaborate together and give distinguished lectures to each other within your countries. And also Professor Spencer is going to help us to identify other professors within the disciplines that you are all partaking, to see if they can offer themselves to come down and give you some, to be part of this series, so that you have a different subject every, once a year or twice a year, as much as time will allow for the faculty members from the other countries to come here. Thank you very much, Professor Spencer, for agreeing to start this lecture series for us in East Africa. I work for the National Science Foundation. I'm not here officially, so the reporters are back in the thing. You should not be mentioning me as a national science representative. I am a US government official. I have to be approved by the government to represent the government. I'm not representing the government today. This is a baby that we started with Professor Spencer, and we hope the governments will, in the future, maybe embark on this, because you guys will be showing your interest in having this exist in this region. That's the only way it works. It has to be two-way. We can't all do it from the other side. Thank you so much, Professor Spencer. Now I invite you to the podium.
Well, thank you very much for all these very kind words. I'm very pleased to be here. It's my first time in Uganda. I've seen a lot of wonderful things in the last few days. I'm very much enjoying being here and visiting you all at Makerere University. So I'm going to be taking you on a bit of a tour of things that we've been doing in our laboratory for the last few years. And I call it made to measure surfaces because I think we have the opportunity now to take almost any material and tailor the surface in the way that we do with cloth, to tailor the surface to make it appropriate for a particular application. I'll tell you a bit about what I mean by that in more detail, and I'll give you some examples from our research. Just wondering whether I should stand. Yes, I'll stand up here, then I can use both hands and talk in the microphone. Okay, so what we see here is the main building of my institution after it was built, which was in the mid-19th century. And at that time, Switzerland was a very agricultural country, not a very wealthy country at all, but they had the vision that they needed engineering to get ahead. And there was nobody teaching engineers, none of the universities taught engineering then. And so the federal government of Switzerland founded its institution called the Polytechnicum at that time to be the engineering school of Switzerland and also teach science and architecture. And that's all we teach now. We're not a full university like you are. We have no lawyers, we have no medics, but we have science, engineering, and architecture. And this is still in the central campus. And I'll just tell you a little bit more about the whole situation of the ETH, as we call it. ETH stands for Eidgenössische Technische Hochschule, which is German for the Swiss Federal Institute of Technology. And you may wonder what this is. It's Switzerland. So here are the borders of Switzerland, and you can see that it's surrounded on all sides by other countries: France, Germany, Austria, and Italy, and Liechtenstein is hiding here somewhere too. And when I was looking at this, this morning, I saw it's sort of green, and there are lakes on the western side, and there are also lakes down. This reminds me of another country. This country looks familiar to you, but the Queen Elizabeth Park's down here, and Kenya's over here somewhere. Anyway, I was reminded. This is the inside of our main building, and as I said, it was constructed in the middle of the 19th century by an architect who had just built the opera in Dresden. And then a number of other architects have been involved, but they've all held chairs. They've all been architecture professors at the ETH. This is the back of the building, and just to give you an example of modern architecture out of our institution, you may have seen this a few years ago. This is the Bird's Nest, the main stadium of the Beijing Olympics. And this was designed by two of my colleagues, Herzog and Demont, who have a part-time position. They share the position actually as professors of our institution. And in their spare time, they build things like this. This is the campus where I am, up on a hill above Zurich. Zurich is the city over here. This is Lake Zurich, and in the background here are the Alps. And I sit here and looking up over the forest. We've had a few Nobel Prize winners at the ETH, including people you've probably heard of, like Röntgen, Dubai, Einstein, Pauli, Bloch, Staudinger, and in recent years, Benmont and Müller, famous for their invention of the high-temperature superconductors. And our most recent Nobel Prize winners are in chemistry, Richard Ernst and Kurt Wüttrich, who are still with us, and they made big contributions to NMR, nuclear magnetic resonance. Okay, now for the scientific part. And first of all, an outline. Why do we want to tailor surfaces? How do we tailor surfaces? I'm going to go into some detail on polymer brushes and lubrication. Patterning is another way to tailor surfaces, using SAMs, self-assembled monolayers, and other polymers. And I'll finish off by talking about gradients. And the question came up, how can this be done in Africa? A lot of the techniques I'm going to be talking about are actually very cheap techniques and very simple techniques, and they don't require expensive equipment. The expensive equipment tends to come in characterization rather than the functionalization. But if you're clear that you can clean surfaces, then I don't see any reason why many of these things shouldn't be done here. So, why tailor surfaces? So, the philosophy here is that we start off with a material, and we're normally familiar with bulk properties of the material, and these might be modulus, tensile strength, density, temperature resistance, porosity, and price. Normally when we buy materials, we buy them by the kilogram, not by the square meter. Cloth, I guess, is the exception. Surface properties include things like wettability, anti-fog properties, easy to clean properties, paintability or printability. This is a big deal in the packaging industry and also the automobile industry, where they use more and more polymers in structural components of the automobiles, and then they want to paint them to make them match the rest of the car. Biocompatibility is almost exclusively a surface property, and lubricity. Lubricity is something where we put a lot of effort. And wear resistance, and corrosion resistance. So the idea is to take our ideal bulk material that we decide we need for a particular application, and then think what surface properties does it need, and then somehow we have to impart this to this, and that means doing some kind of surface functionalisation to change the properties of the surface of this to make it suitable for what we want to do. So, next question, how to do it. And I'm just going to tell you the main techniques that we've used in our group for the various applications I'll tell you about later. One of the most important ones over the last years has been self-assembled model layers. And I know there's only one person who confessed to being a chemist here today, but nevertheless there are going to be a few molecules, but I'll try and be gentle with you. So these molecules are basically hydrocarbon. Each one of these is a CH2 unit. And at one end we have a sulfur and a hydrogen, and at the other end we have some function, X, which could be a methyl group, or a hydroxyl group, or an acid group, but really it could be anything we can stick on the end of this chain. But the important part is that we have this sticky end, which is the vial, and we have an end with which we want to functionalize the surface. So let's say we pick the CH3, and we take a lot of these molecules and we expose them to a gold surface. This isn't pure gold. We just evaporate a layer of a few tens of nanometers or hundreds of nanometers onto a silicon wafer. And if we dip that into a solution of this thiol, then the thiol automatically sticks down onto the gold. It's a very strong bond it makes to the gold spontaneously. And these chains here interact by van der Waals interaction, and they lead to a kind of packing that means the whole thing becomes spontaneous and very crystalline. So we have a surface that's just close packed with these chains, all oriented together and presenting this functionality to the outside world. So if we just take this gold surface and dip it into this solution, we produce a concentrated layer of functionality of whatever was stuck to the end of the thiol molecule. And it's a very easy process to do, and we do it every day in our lab. So they look something like this in the end. Here's your functionalized, here's your function, here's your gold, and here's the chains of hydrocarbons that are causing the organization. Now, I'm just going to quickly go through the methods, and I'll go into more detail later. So that was sand. The next thing I want to talk about is polymer brushes. Polymer brushes come about when you take a polymer that has some kind of sticky end again, and you expose it to a surface where the sticky end will attach, and you put it in a good solvent. If it's dry or if it's in a bad solvent, it will collapse. But if it's in a good solvent for this polymer, then if the polymer chains are spaced fairly widely, like this, then they kind of adopt the same shape they would have if they were floating around in solution, except one end's attached to the surface. And we call that the mushroom configuration. But as they get closer and closer together, they want to keep out of each other's way because there's an entropic penalty if they start to interact with each other. And so to avoid that, they stretch out into the solution against the elastic forces, and they become what's called a polymer brush. So you have a whole load of polymer chains that are really stretching themselves to have as much interaction with the solvent as possible and as little interaction with each other. So this is all driven by a combination of entropic and enthalpic forces, but mostly entropic forces. And this is what we call a polymer brush. And so these chains can be any length, but typically they're between 10 and 1,000 nanometers long. Now, there are a number of ways of explaining polymer brushes to people, and one way I like to use is a theatrical approach. And this is at a meeting in England a couple of years ago. This is a lot of scientists pretending to be polymer chains in the polymer brush configuration, so they're pretending they're in a good solvent. And I like this picture because this character here is not a particularly stretched out chain. He's Jacob Klein, who's one of the founders of modern science of polymer brushes. And we have a number of representatives from other groups who work in that area. This is a polymer brush demonstration in Madrid just after they won the European Cup a couple of years ago. Now, there are two ways of making polymer brushes. We can either take a molecule that's ready-made and has some kind of sticky end on it, and we can stick it onto a surface, and that's an example here. In this case, it's not individual chains, but it's chains that are attached to a backbone, and then we stick the backbone on the surface. And there are a number of reasons for doing that, but basically we've synthesized this to start with, and we put it into solution, rather like we did with the thiols, and then we dip in a surface that's going to interact with it, and then we have a polymer brush just by dipping. So it's very easy to make that kind of polymer brush. What's a bit more tricky is to put a layer of initiators onto a surface, and then to do polymer synthesis on the surface. So we actually grow the polymer out of the surface. And obviously that requires more chemistry, more synthetic chemistry, in situ synthetic chemistry. The advantage of doing that is you have complete control over the composition of the brush. You can change the monomer as you grow the polymer, for example, have different functions as you're growing. And you can grow it as long as you like. So you can make really very long polymer chains on the surface to graft from. So grafting to, grafting from is the two approaches. Now, another approach that we've been using more recently to put polymers on surfaces is to use a chemistry called nitrene chemistry. And nitrines are very reactive, short-lived species that will react with anything in their neighborhood. So they just insert themselves into chemical bonds. And what we do is we take a surface and we cover it with something that's going to generate a nitrine at this blob here. And then we spin coat a polymer on top of it. Then we expose it to UV light that generates the nitrines. They react with the polymer, and then we wash away all the polymer that didn't stick. And what we made here is something like a polymer brush. It's not quite as tidy as the polymer brushes I showed you before, because these chains can attach anywhere along their length, not necessarily at their ends. But it's a way of fixing a polymer onto a surface, and if we choose this anchoring group correctly, we can attach a polymer onto almost any surface. It can be another polymer, for example, or a metal, or a ceramic, or anything. And this just, for the chemists, this just shows the one reaction that's important here. We have something, this R group, that attaches it to the surface, and we have this nitrine generator, which is N3 at the end. N3 gives off N2 under UV light, so it's just nitrogen, leaves this short-lived reactive nitrine species, which then inserts into a chemical bond. Any chemical bond could be one of the bonds in the polymer, and then it fixes it onto the surface. So very unselective chemistry, but very useful for attaching almost any polymer to almost anything, and making almost a polymer brush. Now, our main application of polymer brushes has been lubrication. Lubrication we see as being incredibly important to energy saving and CO2 reduction. Most of the energy that gets dissipated in the car ends up being dissipated either in the brakes or in aerodynamics, but a very large portion goes into friction in the engine. If you can reduce that friction, then you save a lot of fuel, and therefore you save a lot of CO2 production as well. So the approach we've been taking is using polymer brushes for lubrication. And these are the characters who've been working on it over the last 10 years. A lot of people from inside the group, a lot of collaborators from outside, a lot of people have helped us financially, both American institutions like the Air Force Office of Scientific Research, Swiss money through the ETH, my institution, and the EMPA, another federal institution. The European Science Foundation helped us too, and more recently Lafarge, which is a big cement producer, has helped us looking at this. You'll see why cement in a little while. And just to give you an idea of the composition of my group, this is sort of a typical group. I should talk closer. Okay. A typical cross-section of my group, these are their nationalities. And you can see almost, we have 2 Swiss, but the rest are from Europe and Asia, the US, so many countries are represented here. This is typical in our group. 70% of the professors in our institution are not Swiss, just to give you an idea of how international the place is. So, I don't want to frighten the non-chemists here, but this is one of the molecules that we've been using a lot, and it's a lot simpler than it looks. We have a backbone, and the backbone has side chains coming off it, which end in this NH2 group. And the NH2 group can be used in 2 ways. If we put it in water, then it just becomes NH3+, and so it picks up the positive charge, so it just becomes a positively charged group. So it's a hydrocarbon chain with a positive charge on the end. But we can also use it to hook on side chains, so this is a long polyethylene glycol side chain. And in the end, it looks something like this. We have a backbone, we have the unused NH2s, which pick up their positive charge, and we have the side chains. These positive charges will stick on a negatively charged surface, and they'll force the side chains out into the good solvent, which in this case is water, so good solvent, polyethylene glycol. And just by dipping, for example, a silicon wafer into a solution of this polymer, which is commercially available now, you have a polymer brush on the surface. And it has lots of interesting properties. It's biocompatible. Proteins won't stick to it, which means cells won't stick to it either. It's a way of making non-fouling surfaces, for example. And it's lubricious, which is why we got interested in it. Now, here's a very straightforward tribological test called the pin on disc test. We use it for testing lubricants, measuring friction. And so we take our lubricant, we put it on top of the disc, and then we slide a pin on it by rotating the disc underneath the pin. We put a load on it, N, which we can do with a dead weight, for example, and then we measure the friction force with a strain gauge as we rotate it. Very standard friction measuring test. And if we take pure water or a buffer solution, then we get a result that looks like this blue curve here. So quite a high value of friction, fairly noisy, and this should be friction coefficient. I'm sorry, this is wrongly labeled, but it's quite a high value of friction coefficient. If we put in the lubricant, the water plus the polymer I was just talking about, which we call PLL peg, we put the PLL peg in there, and we have a much lower value of friction, and it's very steady. If we put just a surface coating of the polymer in there, and we do the experiment underwater, then for the first rotation it lubricates, and then it looks like it's coming off, and we end up with the value of the pure water. And so what's happening, we wanted to investigate more closely, and we used fluorescent labeling in order to do that. We put a green label on one batch of the polymer and a red label on the other one. We absorbed the green label polymer on the surface, and we put the red label polymer in the solution. We did the pin on disc test, and as we did more and more rotations, then more and more red came into the track where the pin had been scraping. In other words, what happens is it heals itself. As we scrape away the green polymer from the surface, the red polymer in the solution comes in and it replaces the green. But it maintains this low value of friction, even though we can see that we're scraping the stuff away. So it's a self-healing lubricating system. Now what's happening when we slide one polymer brush layer over another polymer brush layer? This came from David Klein, the guy who was doing this in the picture I showed you earlier. We have several forces at work. We have osmotic pressure, which will inhibit the compression of these polymer brushes. And then we have more entropic forces that prevent the interdigitation of these chains. Because if they interdigitate, then you restrict the configurational entropy of these polymer chains. And so there's a free energy term that stops that happening. And so there are really two springs, if you like, that stop these two hard surfaces coming together, and they're prevented by these soft surfaces, the polymer brushes. Now at the interface, although it's not obvious from this drawing, the way I've drawn it, there's a fluid film. And that fluid film is there because the concentration of monomer as you move out from the surface is not constant, the way I've drawn it here, but it actually falls off in a parabola. So in the central region where the two brushes meet, there's actually much less monomer than at the walls. And so in the middle, just because of the brush physics, in the middle we have a low concentration of polymer, a higher concentration of solvent. And so that's the fluid film where the sliding happens when we have one brush sliding over another. So we're giving it a fluid film, even in the absence of any hydrodynamic forces, which is what we normally associate with fluid film lubrication. But in this case, even when it's stationary, there's a fluid film there. Now, why am I showing you a picture of the Burj Al Khalifa at this point, you may wonder. And I just wanted to show you this as an example of an application of polymer brushes that we've been looking at recently, and it comes from the cement industry. If you want to build something like this, or even something like this, then you need to move cement up to a height. You need to pump the cement. And this is becoming harder and harder because the cement industry is trying to lower their CO2 footprint because they burn a lot of limestone in order to make the so-called Portland cement that they use to make concrete. And so they're using less and less of this limestone in the final product. Now, when they mix cement, they put in water with some fillers and some cement, with Portland cement, and they're putting less and less of the Portland cement in there, which means they're putting less and less water in. It's not just a diluent of water, it's a reactant. It reacts with the Portland cement to cause the hardening reaction. And that means, as they put more and more filler in, and less Portland cement, and less water, then this slurry is becoming more and more viscous and harder to pump. And the rheology of it is a complicated business because what can happen is, this is the shear rate, so this is the speed, if you like, at which you're trying to pump the cement, and this is the viscosity on this axis, log scale. And as you go to higher and higher speeds of pumping, then you start to get what's called shear thickening, and you need more and more force or you need more energy being put into the pump to be able to pump that concrete. Now that's okay, it's predictable, and you can just turn up the current that's going to the pump. But that's called continuous shear thickening, and that's something that they have under control. What is a real problem for them is if they get what's called discontinuous shear thickening, which is where they get to a certain point and the viscosity increases to infinity. If it increases to infinity, then you just destroy the pump. And you can imagine what happens if you destroy the pump when you have a column of cement which is hardening sitting above it. This is a disaster, and they really want to understand this, and they really want to avoid this. So this is a Newtonian flow region, this is continuous shear thickening, this is discontinuous shear thickening. And there has not been any theory that's really connected these or explained all of these until now. And so we started looking at it in a rather different way. We started thinking not about the fluid as a fluid, thinking about it as rheology, but we started thinking about it as a collection of particles that are sliding over each other, and then it becomes a tribological problem, a lubrication issue, as much as a rheological issue. Now, this is a lubrication curve, and this is called the Strybeck curve, and it's sort of fundamental to lubrication theory. And it shows the friction coefficient on this axis, and if you like, the speed, but not just the speed, it's actually this number on the x-axis. It's a dimensionless number, but it includes the speed, it includes the load, and it includes the viscosity. But if we just think about it as the speed changing for now, when we're at very low speeds, we don't have any hydrodynamic lift. And so that means the two surfaces, and we can just think about macroscopic surfaces, say 2 pieces of steel and oil right now. When you're at very low speeds, then the surfaces just rub against each other. There's no hydrodynamic lift at all. And hydrodynamic lift you can think of as the sort of lift people get when they're water skiing. It's what keeps you above the water when you're water skiing. And when you stop the speedboat, then you sink down into the water. There's no hydrodynamic lift. Now, as you go to higher and higher speeds, then you start to get hydrodynamic lift, and the friction coefficient goes up just because of the viscosity. As things slide faster in a viscous medium, the drag goes up. That's why boats don't go infinitely fast. And so your viscosity goes up as you increase the speed. Now there's a transition between these two called the mixed regime, where part of the surface is in the boundary regime where they're touching each other, and part of the surface is in hydrodynamic regime where it's being lifted. So that's just the interface between these two regimes. But this is a very commonly seen behavior in bearings, for example, and very common for the lubrication engineer to use this. But it's never been used before to look at particles. When people think about particles, they think about particle collisions and momentum transfer. And so what we did is we tried to make a connection between these two areas and think of, this is the regime where we have the Newtonian plateau I showed you earlier. And this is when we start to go too fast and we bang the particles into each other and we push the particles into a boundary lubrication regime. Now there's a lot of theory on granular materials, and we just made a mathematical relationship between the lubrication theory and the granular materials theory so that we could start to model the whole process using a contact dynamics approach. Now, the contact dynamics simulation, which we did together with our colleague Hans Hermann in our civil engineering department, we could put in the boundary lubrication parameters, the hydrodynamic theory, and just try and calculate using lubrication theory what was going on when particles were flowing past each other. And we managed to use that, just those two behaviors, hydrodynamic and boundary, to explain this discontinuous and continuous shear thickening. As you see, we have the Newtonian flow reproduced down here. So this is the model based on lubrication theory, and we could reproduce the continuous shear thickening as we went to higher speeds. But what we also found is that when we went to very high speeds, we could actually reproduce the discontinuous shear thickening as well. And by changing the friction coefficient, we could move from continuous to discontinuous shear thickening. So it seems like if you lower the friction coefficient between these two cement particles when they collide with each other, then you can avoid getting into the discontinuous shear thickening. So this is very promising because it seems like just by adding a polymer that will lower the friction on the surface of these grains, we could cause the cement slurry to behave in a more well-behaved way. Now, we were able to tune the surface, in the lab we were able to tune the surface friction of these cement grains by putting in the kind of polymer brushes I was talking about before. They just spontaneously stick to the surface of the cement grains. We were able to vary our boundary lubrication friction coefficient between these values. And we could see how well the grains were sliding over each other by making a slurry of grains and then centrifuging it. And the better they slid over each other, then the more the grains would pack. And we could actually use this as a very quick and reliable way of seeing how efficient the cement slurry was being able to flow over itself. And here's the final result. This is actually data, this is not simulation, so we could actually see that as we changed the friction on the cement grains, we went from a more continuous shear thickening into a discontinuous shear thickening kind of behavior. Here we have a friction coefficient of 0.57, but as we go to a friction coefficient of 0.51, then we can push it from discontinuous to continuous, and therefore much better behaved cement slurry. So just to conclude what we could get out of these experiments and modeling, we could make a direct connection between the transitions in the flow regimes and those in lubrication regimes, so connection between tribology and rheology. We showed that the friction determines the maximum volume fraction in boundary lubricated flows, and we could, by controlling the lubrication, we could control the onset of the nature of the shear thickening transition. And the bottom line is that with better polymer brush lubricant additives, we could make the cement flow better. Now, why am I showing you a picture of Lady Gaga and Ronnie Spector and the Ronettes at this point? Partly for a break from the science, and partly because this is another application of polymer brushes. Conditioners, hair conditioners, involve polymer brushes. The brushes spontaneously stick onto your hair. Your hair is negatively charged when it's in water. There are positively charged brushes that will stick onto your hair, and that's what makes it feel lubricious when you put hair conditioner on your hair. And without hair conditioner, this kind of hairstyle is quite difficult to achieve. Okay, back to the science. After doing a lot with lubrication in water, we started looking at lubricating in oil. Obviously, oil lubrication is more relevant, especially when it comes to the automobile industry. And this was no longer really a possibility. We couldn't use charge to attach our polymers to the surfaces anymore. So we decided to use this grafting from root, where we put initiators on the surface and then we grew polymer chains out of the surface. And we used a technique called atom transfer radical polymerization, invented by this character Chris Matuszewski in the United States. And the important thing about it is, don't worry about the chemistry for now, the important thing about it is it's very controllable, it's very it leads to very low polydispersity, which means all the chains have the same length, which is what we want. And it's relatively straightforward to do on the surface. So we immobilize our initiator, and then we do the polymerization reaction and grow the chains out from the surface. And we wanted these chains to be oil compatible, so they had to be soluble in hydrocarbons, like motor oil. And in order to make chains on the side of the monomer. So this is the bit that polymerizes. This is what's known as an acrylate, which polymerizes very nicely by this ATRP technique. And then onto the acrylate we hooked a side chain. And that meant that while this was polymerizing, it was producing a sort of Christmas tree structure where every monomer led to a side chain sticking out of the side. So we had this sort of structure coming out of the surface. And we had 3 different lengths of side chains just to see which worked the best in the kind of model oils we chose. Now, if we look at a number of different oils and their performance, here we have an example of a borosilicate bead sliding against a silicon wafer with no brush. There's no polymer in this top data I'm showing you here. And we see the Strybeck curve behavior again. Out here we have the boundary regime where we have the hard borosilicate bead just sliding against the silicon wafer with no hydrodynamic lift, so it's quite high friction and quite noisy. And the viscosity is now in the x-axis, so we can plot all of these on the same graph. And these numbers here just show the viscosity in centistokes. X-decking is about 4 centistokes, so it's very viscous. And then we have some oils which have higher viscosity. But it all goes nicely on a single curve. And out here is the hydrodynamic regime where we've got the hydrodynamic lift caused by the viscosity of the oil. So that's just oil and 2 hard surfaces with no brushes. Now I'm going to compare that with putting the oil-compatible brushes that we grew on the surface. And you can see an enormous decrease. This is a log scale here. So we've got more than a factor of 10 decrease in friction coefficient. And what's also interesting is this hydrodynamic regime gets extended and then goes straight into a low friction regime. So there's no mixed regime anymore because there's no hard contact going on. We just go straight from hydrodynamics out here to a fluid film that is caused by the behavior of the brush visitors. So this is a very interesting development as far as we're concerned, and we're continuing to pursue it and looking at wear issues which have to be borne in mind and various practical applications. And the first application of this was for a very Swiss industry, for the watch industry, where they have very low speed. They don't have high loads in watches, but they have very low speeds. And because there are such low speeds, they're usually at this side of the curve, so they have to worry about boundary lubrication. But with polymer brushes there, they can get an order of magnitude less friction. And with an order of magnitude less friction, if you've got a battery-powered watch, that means you get 10 times longer life for your battery. So there are a lot of good reasons for wanting to do that. Okay, so moving on to something very different now, and that's patterning. We've always been involved in patterning. We want to pattern surfaces so we can have different things at different areas of the surface and use them for biosensors, use them for testing, biological fluids, whatever. And so patterning has always been important to us. These are the people who've been involved in the patterning. Former PhD student, former postdoc of mine who's now a professor in India, former PhD student who's now a professor in China, a colleague of mine, a long-term permanent colleague who's an expert in X-ray photoelectron spectroscopy. This is a colleague who started a company once he left my lab. He now sells polymers that he makes in this company. This is a student who just finished in my group, who's now looking for a job. Now, first of all, I'm going to just talk about ultra-flat metal patterns because it turns out you can do a lot of interesting things with them. And by ultra-flat metal patterns, I mean a completely flat surface where we have a pattern of different metals in the surface. So there's no topography, no structure in the surface at all. They're very flat on a nanometer scale, and yet some areas, on a regular pattern, some areas are a different metal. And you'll see what I mean in a moment. The way we make ultra-flat metals is we start off with an ultra-flat surface, like a silicon wafer, which has an inherent flatness of around a nanometer. We silanize it. We silanize it because we don't want what we put on next to stick to it very, very well. Then we do photolithography to make a pattern of holes in the surface. And then we, first of all, we deposit some titanium through these holes onto the silicon surface. And then we deposit some gold on top of that titanium. And then we deposit more gold to fill in all of the gaps here. And so we now have titanium covered with gold, and the whole thing's in the background of gold. And then we put some some sort of support on the back of it. And then we turn the whole thing upside down, and we take off the initial silicon wafer that we used, which gave it a flat surface. So we've got a super flat surface under there. So it's now turned upside down. Here's the surface that used to be in contact with the silicon wafer, and we have a pattern of titanium within a gold background. And titanium and gold have completely different surface chemistries, so we can functionalize them in completely complementary and orthogonal ways at the same time. And this just shows the surface we made. This is under a light microscope. Here we've analyzed it with X-ray photoelectron spectroscopy, and you can see the area that is titanium has a very low signal and a very high signal in the gold area, the gold peak. And here we use time of flight secondary ion mass spectrometry to look at the titanium pattern and the gold pattern, and you can see they're complementary because we've got titanium in gold. And we use atomic force microscopy in order to look across the interface between the titanium and gold just to see how flat it was. You can see the interfaces, you can just about see it, but it's on the 1 nanometer level, the interface. So we really have very flat surface, which we can now functionalize with chemical means. The reason why we see a different behavior in XPS and top sims is the XPS doesn't actually have this high resolution as top sims. Top sims has a resolution of about 150 nanometers, something like that. So very high spatial resolution technique. Whereas gold is a less high resolution with a few nanometers, and so it shows a bit of a continuous transition here. But this is a reflection of what we actually have here, a very sharp edge between the titanium and the gold. Now, what we can do at that point is we can use two different molecules that will function. One will functionalize the gold, one will functionalize the titanium. The stuff that's functionalizing the titanium I'll talk more about later, but it's nitrodopamine, and on the gold we're using a thiol, and it's OH terminated, so it's very hydrophilic, and what we put on the titanium is very hydrophobic, and you can see that in the water droplets that condensed here from the vapor phase. This is hydrophilic and this is hydrophobic. We put them on at the same time, so you can functionalize different areas of the surface at the same time, just in one plot. Now, another way of making patterns also uses photolithography, but it's doing it with polymers. So here we're using our nitrines that I told you about earlier. We put our nitrine generating layer, we spin coat polystyrene on top of it, and then we put a mask on top of that to filter, to pattern the UV light that then we shine through. The UV comes through, activates the nitrines here, they stick onto the polystyrene. In this area, we don't activate them, so they don't stick. Then we wash it, and all the polymer comes off except the chains that were in close contact with the nitrines that saw the UV light. We then do the whole thing again. We spin coat another polymer on top of it, in this case polyvinyl pyrrolidone, which is very hydrophilic and very resistant to protein and cell adhesion. And we expose it without a mask, and all the areas that weren't hit before with the UV light now become activated, and they connect to the PPP. Then we wash away the excess PPP, and we've got two polymers in a pattern on the surface. And then we use it for cell experiments. We expose it to either directly to different cells in serum, or first of all we coat it with a particular protein that we know facilitates cell adhesion, and then we expose it to the cells. And here you can't see terribly well. This shows, this you can see better. Let's just look at this side. So here we've taken two different size of patterns. One is 20 micrometers, one's 75 micrometers, and we've exposed it to osteoblasts, which are bone cells, and then we've stained it with things that stain different components of the cell. So the blue is actually the cell nucleus, and the green is the mechanism that the cell uses for sticking to the surface. And here you can see we've managed to isolate a single cell on the surface, and with the bigger pattern we have multiple cells. And cell biologists sometimes like to do multiple cell experiments, sometimes single cell, and so they have the choice here of which they use. Now, the last topic I'm going to talk about is gradients, and this is the team who's been working on gradients, and as you can see, it's a gradient. It's actually more of a gradient than you might think, because it's actually a gender gradient as well, more boys at this end and more girls at this end. And we started off using the alkane thiles I mentioned before, and this is one of the things that you can really do anywhere. So you just need a clean gold surface, and you do that by evaporating in a vacuum system. So you have a clean gold surface. You can even buy clean gold surfaces that you then strip off a template, like I described with the ultra-flat surfaces. And then you take your clean surface and you dip it into a solution of one of your thiles. And you dip it in slowly. And if you dip it in slowly, then because the adsorption has a certain kinetics, the leading edge will have a higher concentration than the trailing edge. And then you just immerse it quickly into the second adsorbate, and now you're doing gradient. At this end, you've got the first component in high concentration. At this end, you've got the second component. Just to show you what I did in a diagram, this was the first dip where we had a high concentration at this end and a low concentration at this end. And then you plunge it into the second component, and you fill in all the gaps that you have here with the second component. And now you have a gradient in surface chemistry from one end to the other. Now, if you make that surface chemistry to have different wettabilities, that means that you can have a hydrophobic behavior at this end and hydrophilic behavior at this end. So not wettable at this end and very wettable at this end. And you can use this for a number of different things. You can look at the effective wettability on some process, like the adhesion of bacteria to a surface, or the behavior of cells on a surface, or tribological behavior. But you've got all of these different surface chemistries there on a single sample, and that means that it's like doing a high throughput experiment to examine one of these gradients. And we also made two-dimensional gradients where we have three components in there. In this case, we had a fluorine-containing component, a hydrocarbon-containing component, and a hydrophilic component. And we've measured all of these things with different techniques, including XDS. And here we made a charge gradient. We have one component that is terminated in COOH, which picks up a negative charge in water, and one component was terminated in NH2, which has a positive charge in water, and then we attached differently charged beads onto the surface, and depending where we were on the surface, we had different concentrations of beads. And this can be extended to proteins too. Proteins have different charges, so different proteins would absorb in different parts of our two-dimensional gradient surface. Now, I briefly mentioned we absorb other things than files on surfaces, because files will really only stick to a restricted number of expensive metals. If you want to functionalize something like titanium or iron, then you use different surface chemistries. And what's very good for titanium and iron is these nitrodopamines. This is based on the chemistry that mussels use when they stick to rocks in the sea. So they make very strong bonds with all kinds of different surfaces. And we've made them in hydrophobic varieties and hydrophilic varieties, and we can actually make a hydrophobicity gradient using these things too, by the same dipping process I talked about with the thiles. I showed you this one before. This was where we used nitrodopamines here and thiles here, but you can actually do that in a gradient too. Now, in this case, we have a patterned surface with the titanium circles within the gold matrix. And we've done the dipping in two directions, one after the other. So we have a gradient on the gold that goes from hydrophilic at this end to hydrophobic at this end. And we have a gradient on the titanium that goes from hydrophilic at this end to hydrophobic at this end. And what I'll finish up talking about is morphology gradients. So in cell biology, and something that interests us very much is what you have to do to a surface to make it a good implant surface. For a hip implant or a tooth implant, what makes bone cells want to stick to it. And this is very important in the implant industry, and the implant industry is quite big in Switzerland, and we've had a lot of conversations with them about it. And it's not just the surface chemistry that is important. They already know that titanium, for example, is a very good material for integrating with bone. So a lot of implants these days are made with titanium alloys. They have good bulk properties, but also the titanium surface has good surface properties for interacting with bone, just without any treatment. But one thing people have found is that different kinds of roughness work differently when it comes to bone integration onto the titanium surface. And so we want to look at morphology or roughness, but we didn't want to look at one roughness after another. We wanted to make a gradient of roughness so we could look at all of the roughnesses in one experiment to see how the cells were interacting with these different values of roughness. And the way we did that first was we took an aluminium sheet and we sandblasted it. So just a regular sandblaster that you find in the machine shop to make it rough on the micrometer scale. But then we polished it using our dipping machine again. We dipped it into a chemical polishing solution, and because the chemical polishing has a certain time dependence, the longer it's in there, the more polished it gets, then by dipping it slowly, you can make one end more polished than the other. And that's what we did. We just dipped our sample into the chemical polishing solution. So again, it was using the same apparatus, withdrawing it actually this time from the polishing solution, and this end was more polished than this end. And this is what it looks like under the electron microscope. This is the unpolished end, and this is the one that's been in the polishing solution long. So you can see the change in roughness here. And this is a measurement we did using laser profilometry, and you can see how the roughness is changing from one end of the sample to the other. And we filtered it at different wavelength, using different wavelength windows, because different wavelengths affect the cells in different ways. So we actually Fourier transform the data and then look at the change in roughness with position. And this shows the way it gets polished. This is a diagram of the roughness after sandblasting, and then you can see which bits are leaving first. These are the different roughness wavelengths. If you look at the lowest wavelength, so the sharpest parts, they're the ones that disappear first because they're the most reactive to the chemical polishing solution. Now, in biology, I know most of you don't do biology, but a big difference between physics or physical chemistry, which is where I come from, and biology is that in biology you have to do statistics. So you don't do one experiment, you always have to do loads of replicates, and then you look at statistical changes just because life's like that. It's not like physics. I mean, in physics you do 3, you take the average. But in biology, you have to do a lot more. And so we needed statistics, so we needed a lot of identical samples. And what I just described to you, sandblasting stuff, you can't make the same surface twice, obviously, if you sandblast it. And so what we decided to do is make a master by sandblasting and the chemical polishing technique, and then use that as a master to produce identical replicas. And the way we did that is we take the kind of stuff that people use to take impressions of teeth. It's a polymer called polyvinyl siloxane. And we use that to make a negative of the surface. And so now we have a negative. And then we used epoxy resin to make a positive from that negative. And then we turn it upside down once we've separated it from the negative. And we sputter coat it with titanium oxide to make it look like a titanium oxide surface, which is what you have on the surface of an implant, which is made of titanium. It has a natural titanium oxide surface. So this has the surface chemistry of a titanium implant, but it has our predefined morphology gradient. And we can make as many of these as we like from the original master. So we can make identical but still stochastically rough surfaces with a roughness gradient. And you can see the reproduction with the replication technique is very effective. And this is one of the replicas that's already been coated by 16 nanometers of titanium, and we made loads of them. On each replica, we then measured at 3 points at each roughness value, and so we got lots of data that we could then do statistics on. And then if you look at then we put them in a cell culture. These were bone cells from rats, and we looked at the proliferation of these bone cells, how they're reproducing on the surface, and we looked at the effect of the roughness. So as we go along the sample, the roughness is changing, and this shows the number of cells as a function of the time. So the blue color ones are after 7 days, and you can see there's an enormous difference between the rough end here and the smooth end in terms of the number of cells. So roughness has an incredible effect on the proliferation of these bone cells. And if you look in the optical microscope and you stain them, it's even more obvious. These are all the same scale. This shows the smooth end, and this shows the rough end. So you can see there are hundreds of cells here, but at this end, very few cells. Now those were microscale roughness gradients. We also wanted to see what happens on the nanometer scale, because we had a feeling that maybe on the nanometer scale, the roughness interacted in a different way with the cells. And so we made and you can't use sandblasting to make things rough on the nanometer scale. There's no, if you have nanoparticles, they have no momentum, so they're not going to do anything to an aluminum surface. So we have to use a completely different technique. We used a silicon wafer as our base, and then we took a polymer which has a positive charge, polyethylene, and we dipped our wafer into it. And the reason we did that is we wanted to have a positively charged surface. And the reason we wanted a positively charged surface is we then wanted to be able to dip it into a suspension of silica nanoparticles that would then stick electrostatically onto this positively charged surface. And we used our favorite tool here, our linear motion drive, and we dipped it in slowly, and they stuck to the surface, but the longer it's in there, the more nanoparticles stick, and so if we dip it in slowly, then we have more nanoparticles at one end than the other, so we have a roughness gradient on the nanometer scale. And we don't want that polymer there, it was only there to help us make the gradient, so we burn it out. We put it in a furnace, we burn away the polymer, and we turn up the temperature even higher, so we actually get sintering of the nanoparticles into the silicon oxide on the surface of the polymer, and then the thing is fixed. Those particles aren't going to come off anymore. It's just a pure silica surface with a roughness gradient on a nanometer scale. This is what it looks like as you go along it with an electron microscope. You can see the change in particle density from one end to the other. This is how they look after they've been sintered into the surface. So this is where we normally stop the sintering, and they're kind of half gone. Here we've gone too far. Now this shows what happens when you expose them to the bone cells. Again, we have an enormous difference from one end to the other. But the surprising thing is it's the opposite difference from what we saw on the micrometer scale. At the flat end, we have cells. We have about the same number of cells we have on the flat end of the microscale gradient, which is good because they're both flat. But as we go to more and more nanoparticles, we actually see fewer and fewer cells. So on the nanometer scale, the more nanoparticles you have on there, the fewer cells want to stick. And when you have the highest density, you really have hardly any cells sticking at all. The blue color here represents the nuclei of the cells, so it's a good way to count them. At this end, we don't see any cells at all. So the nanoparticles almost completely inhibited. So the nanoscale and microscale seem to work differently. What we wanted to see next is, do they work together? We've only looked at them independently. Can we have two different kinds of roughness on the surface and look at their behavior independently? So for that, we wanted to have an orthogonal gradient where we had a nanometer scale gradient in one direction and orthogonal to that, a micrometer scale gradient. And we had to use a different base material. We couldn't use polymers anymore because we need to do the sintering. I'm just about to finish, so we're almost done. So instead of using the epoxy, we used ceramic techniques. We used an alumina slurry. We made a ceramic replica of our initial negative. So we had a piece of ceramic with a roughness gradient, which wasn't exactly what we wanted. It was only the microscale roughness. So we took that, and then we covered it with silica, with sputtering. We put the PEI on it again to make it positively charged. And then we dipped it orthogonal to the microscale gradient. We dipped it into the nanoparticles. They stuck on the surface in the gradient. We sintered it, and then we had our orthogonal nanometer and micrometer scale roughness gradient. And this is what it looked like before sintering. This is what it looks like after sintering. And then this is what the results look like when we expose it to the bone cells, and we start to measure what's called osteopontin, which is a marker for whether the cells are starting to mineralize, starting to make bone. And you can see that as you change, this is the microscale gradient, this is the nanoscale gradient, as you go up in roughness in the microscale gradient, you get more and more osteopontin produced, so more and more bone mineralization is happening. So the micrometer scale roughness seems to be important. But what's interesting is at this end of the microscale gradient, if we look at the nanoscale gradient, we also have an optimum in nanoscale roughness on top of the microscale roughness, which seems to be interacting and causing more osteopontin production. So there seems to be some kind of synergistic behavior between the two scales of roughness. Okay, so one nice thing you can do with gradients is you can cause things to happen. You can either use it as a library of different surface properties, or you can actually use the gradient to make something move. And what I'm going to show you is a droplet moving on a wetability gradient. And here is our gradient. It's the vial gradient with hydrophobic at this end, hydrophilic at this end. And this is a syringe with water in it. Here comes a water droplet. and it's caused to move along here because at this end it has no interaction with the surface, but at the hydrophilic end it's making hydrogen bonds, so it's incentive. But the question is, can we actually use this chemistry to drive it uphill? So can chemistry beat physics? I hate to put it like that, but no. And of course, the answer is fairly obvious. Okay, so I've taken you on a little tour of what we've been doing over the last few years, and I started out talking about surfaces versus bulk and why we want to functionalize surfaces. Talked about self-assembling monolayers or SAMs and how we can use those to tune the chemical species that is present on the surface and make a close-packed functionality on many different kinds of surfaces, starting with gold, but now many different surfaces. Then I talked about polymer brushes and how we can use those to make surfaces lubricious and biocompatible, and the different ways in which we can make polymer brushes, how polymer brushes can lubricate surfaces due to this fluid film that's at the interface of the two polymer brushes, thereby for entropic reasons, and then how we can use polymer brushes to influence rheology by changing the tribological properties of the grains as they slide past each other in cement. I talked about oil-compatible brushes where we have these hydrocarbon side chains and we can make surfaces much more lubricious by having the long polymer chains on the surfaces. Talked about how we can really lower the coefficient of friction by an order of magnitude at low speeds by putting these polymer brushes in the presence of oil. And then got into patterning and how we can use either metal techniques or polymer techniques to make pads on surfaces of different sizes that have different chemical properties, or different metals that we can functionalize with different chemicals at the same time, or using the nitrine chemistry to make different polymer patterns on surfaces. Then I talked about chemical gradients, how we can functionalize the surface with different wettabilities, which can be used for a number of different purposes. And we can functionalize them also orthogonally to look at two effects at once. And then morphological gradients on the micrometer scale, on the nanometer scale, and how we can use those to look at cell behavior as a function of roughness. And finally, I talked about how we can combine nano and micrometer roughnesses to look at their synergistic effect on cell integration. And I'll leave you with a picture of my group, which we took at our last outing, which was to Sicily, the southern tip of Italy. I had a wonderful few days talking about our work there and also sitting out in the evening sun enjoying the wonderful scenery down there. Thank you all very much for your attention. We have a chance.